Right, let's make a start then. We will have some more copies of the handouts coming through shortly, and they'll be available for you. Right, let's move on now. George Davis is going to bring us Breach the Gap from NPL high base to DEUCE. Tell us about the DEUCE method. George, let me just wire you up.
Oh, I see.
You on?
Right. I did have a thing to draw. What was there? Where do you think it would be? Rather difficult ones, dodging around to see people around the head. That's like about here.
There's a bit of.
Oh, that's fine, that's absolutely superb, yes. I don't know that I get to do what I should try to do. You can't actually reach it at all. Okay. And I'm George Davis. I was recruited by English Electric in middle of 1950 to join the English Electric study team at National Physical Laboratory, helping with the development of the pilot vase. Recruited by Colin Haley, I believe you see here today. He reckons he's retired from a position where he no longer stands up and gives talks, but I expect if there are any rather old and difficult questions, he might well join in with some of the answers. And shortly afterwards, rather sadly, I became the leading English representative for most of the time I was there, which went on until early 1956, when I went up to London to take charge of the English Electric London Computing Service based on a DEUCE in English Electric House there, which was the headquarters of the company. Now, I've got some slides which I'm going to guide my presentation to, if I can find them. Certainly, oh, there they are. They've got up on the table. Now, we talked about DEUCE installations. There were quite a few, as several people have said, and we'll start off like that and see it come up back to front behind. Is it? Yes. We reckon there are about 33 DEUCEs installed altogether, various places, and you'll see 12 of those, about a third of the total, were within the English Electric Group itself. And although the start of English Electric involvement goes back to prehistory, it's quite clear that using computers for its own internal purposes was as much a motive as the possibility of having a product. widely spread around, used particularly for design work, also for other purposes, but that was part of the game as far as English Electric was concerned. I have somewhere to put this back. Now. And I've made some lists of these which are of variable interest within English Electric, mainly in places where they were designing things, interesting things in Liverpool works in various places that I think we'll be hearing from various colleagues. They went on to be used for all sorts of design, production control purposes, and within the one at Stafford Works, certainly for heavy industrial payrolls and that sort of thing. So they did vary in the sort of thing they were used for. Government, National Physical Laboratory, they couldn't get theirs delivered when they wanted to, and they got it in a particular financial year, had to be so. They managed to deliver the large tub called a mushroom in which the delay lines were stored and charged them the full price for that, and then gave them the rest of the computer free 2 months later, by which time they wouldn't have had the money to pay for it. And of course, to Curtin Daisy, very well known people who know these sort of things, R.E. Farber had done all sorts of analysis of aircraft trials and so on. R.E. Bedford Aldermaster, don't know what they did with it there. And you'll see Minibank processing farmers' subsidies and returns, and goodness knows what. They were very heavily information processing. And I've known about this one ever since last week. Regent Centralen in Oslo have one, which I guess must be a government department with a name like that. So I added it to that list for want of any other. And in fact, here we are. The other overseas one was in the university sector. New South Wales University of Technology, now actually University of New South Wales in Sydney, and suffered from very heavy humidity in the late summer, particularly at weekends when they switched off the air conditioning, came in, it wasn't too good. It came to be known rather than University of Technology Computer, unable to evaluate correctly on Mondays. And Queen's passed. And well, as Liverpool, Andrew Young, a rather fearsome character, the later sold it to North Staffordshire Polytechnic, Glasgow. And up here you'll see, apart from the ones I rather switched through on English Electric, aircraft at Wharton in Lancashire, they obviously were heavy users of the sort of matrix systems that Tom was talking about. Certainly, that was a very big influence in quite a few of the uses that were getting out. Because Bristol Aircraft, to say that NPL initiated the matrix scheme and English Electric delivered the computer, is probably John Hard from Bristol Aircraft kicking people in the shins, was originating the matrix scheme as much as anyone else, so he was entitled to get his machines returned with the matrix scheme running. C.G. Black's side, one of the ones that had magnetic tape, I remember, and certainly the only one, the computer room covered with a red carpet. Now, I think that's the main one out of that. One thing I'd like to show you is what the thing looked like. We've had lots of looks at what the Tyler base looked like. And oh, I see. No, it's okay. I've got 2 copies or something, which is the one I've got, I think. slightly gone astray. Very difficult to keep track of these things. Will it turn up? Oh, here it is, yes. Sorry, it's stuck on the back of something else. How does that look? Is it any good? Can you see it? Yes, it's a bit low. There is Brenda Weber. That is the NPL computer. When the ceremony handing over this machine to the director of NPL, you were going to have chairman of English Electric, but then couldn't make it, and it came down not with the director of research or Will Scott, my boss, but it was me handing it over to Sir Edward Bullard, and he said, why hasn't it got your name on it? Well, nonsense, you do it on your railway engine, and that is this rather heavy, butch sort of logo taken directly off a railway engine. Balance the machine in this direction. I think that was the only one we dared put it on. Now, it's got in heavily. So that is that one. Let's see if we... There are various photographs taken of the available ones we have to use. That is not what the dog I'm looking for. Now, here is the one in English Electric House that I left to take charge of. I was mentioning. And there oh, that's the object in the background. You can see it roughly, and you can. Has it gone? Yes. There we are. If you just hold it up. Thanks very much. No, that's fine. There we are. Those arranged in a circle with their electronic stuff on the inside. You just do that. That screw is for hanging the electronic box on, and they all went round in a circle in this thermostatic container called the mushroom for reasons.
I thought we called it a dustbin.
I think that rings a bell. What is it?
Dustbin.
Oh, I'm sorry. You can't tell, can you? Anyway, different people. There we are. And the reader of punch there, and the control panel more or less directly from the pilot ace, the whole thing. The input-output took a U-turn back again, as we'll be hearing later. Massive, great power supply thing. And this was in English Electric House. Well, that was Marconi House then, it became English Electric House. And through this wall was all that remained of the Gaiety Theatre. We went in there occasionally, climbed up through the sort of upper circle entrance, right up to the top. You got there and you appeared, all the rails got right down, not to the stage, but to the space under the stage, because the stage was all gone. And I had the stage doorkeeper's office with the secretary upstairs, a dressing room and lavatory locked together for our 7 programmers that we then had. There we are. Now, we can look at one or two other photographs which are rather more technically informative. Now this one, the rather dramatic one, which has 2 of the people key in the design of DEUCE. Reg Allmark here, he was very concerned with KDF9 later. Here is John Boothroyd. But you see, there's the panel. Here are the doors that open, and there are the individual chassis. And they, the content of one of those chassis is very like the content about 25 valves and accompanying circuitry that you saw in the slices, if you remember, on the pilot days. Why they were converted from things that shape to things that shape, I don't know. Maybe someone here does. And whether it made any difference, I don't know. But they were effectively the same, with the valves, I think, going inwards and all the circuits on the outside. So that gives you an idea. And then the next one, where's it gone? So there we are. Let's try and see what that is. What's that look like? No, that's right. This is the one. What? Oh, thank you. Yes, where did you find it?
Wrong way up.
Yes, wrong way up. Okay, there we are.
Inside.
I think it goes that way. Anyway, This is the inside, and you can walk inside, you can see, and there's the back of the control panel there, with all the wiring for the control panel. Here you see these sides with the valves all sticking in. Down here, these very great big valves for driving the drum, and there is the drum, 8,000 word drum, 16 heads, each has 16 positions, so you've got 256 tracks, 32 words each track, 8,000 word drum, which I think is twice what was on the Pilot Ace, roughly equal to one of the 4 drums on the Big Ace. So those are the photos that give you an idea of how the thing looked when it was working. I think that I allowed myself 15 minutes to start the thing. Originally, we did find, I should explain, in running this seminar, and I was told off by the CCS committee to run it, being the one from this area of endeavour on the committee. And there are very few of my colleagues from English Electric who've got in a position to contribute, including people on the engineering and so except the development side. But I have managed to persuade 4 of my colleagues who've been very concerned with different areas of application to help out here and make various comparatively brief contributions covering different areas of application and interest. So perhaps if they'd like to come up in turn and do their bit, then maybe we can get together at the end.
Right.
How am I doing time?
Right.
Is that about right?
That's about it, yes.
That was about right.
Yes.
I didn't want to be too short.
I wasn't going to allow you to be too long.
No, people can squeeze it, I've noticed.
Right, and Mr. Dennison next, is it?
John Dennison, who came down from Stafford and joined the NPL doing application on Pilot Ace and for.
Well, although I'm supposed to be talking about engineering applications of the DEUCE, the story really starts with the Pilot Ace. I was in the mathematical physics department of NRL in English Electric, and I was seconded to the NPL to learn how to program the Pilot Ace. And immediately there was a flood of requests for engineering jobs to be done on the Pilot Ace. I think perhaps the first of those, well, I should say that the aircraft industry especially were interested in methods of computation, fast methods of computation. And we had an aircraft division at Wharton, and they used to send jobs. The first of which I think was the calculation of supersonic drag on an aircraft fuselage. That involved double integration of a fairly complicated function. And at that time, there was no drum on the machine, but we managed to program that using recursive methods for the integration. Now, Tom Vickers has given me a good lead-in for one of the other topics, and that is the solution of large sets of simultaneous equations. I think that the set that he was referring to came from Wharton. It was a set of equations involved in the structural analysis of the fuselage of a plane. And in fact, as Tom said, we solved this set of equations by, in fact, a week of nights using 80,000 cards. And we did several of these, in fact. On one occasion, unfortunately, 2 of the cards were interchanged in the middle of the process, and we had to put the cards through a collator, because fortunately they were all numbered, and we found out where the swap had occurred, and we managed to start again from there. They also asked for other calculations, such as flutter calculations on the wings, and they were key customers for the matrix schemes that Tom has also mentioned. Now, from Stafford, there were problems from the electrical engineering side of the industry. One of these arose from an incident that occurred in the late 40s. An alternator rotor had disintegrated on overspeed test, and it was thought at the time that this was due to it running at a critical speed. That's a speed at which any slight curvature in the shaft will be exaggerated, will grow, and the shaft will run itself to pieces. And so a long investigation into the calculation of critical speed was started. At that time, the first critical speed of a shaft could fairly easily be calculated in the drawing office, but they had difficulty calculating higher ones. And before the work on on computers, we had a number of mathematical assistants churning away on Brunswigas, as has also been described earlier. In fact, one of them was so enthusiastic that he broke off the catch, which was supposed to prevent the handle from going around the second time. We managed to do some calculation, but when the opportunity for using a computer came along, we were asked to write a program using the Microstat-Holzer method. This involved splitting the shaft up into discrete sections, using a transfer matrix, taking a particular speed, starting at one end of the shaft, finding out what the conditions were at the other end, and then adjusting the speed to make the conditions right. And in fact, that program was used very frequently for the calculation of the critical speeds of the shafts produced in Stafford, and eventually to calculating the critical speeds of a whole line out of shafts for a turbine, alternator, exciter combination. So you might have 7 shafts on up to 14 bearings, and it will cope with that. Well, I mentioned these because this was the start of the use of, first of all, the pilot ace, and then the DEUCE for engineering purposes. And the critical speed program, for example, was translated to the DEUCE, and again used quite a lot. Another problem arising in Stafford was that of the behavior of circuits involving rectifiers, and a program was written for studying the behavior of the current in the rectifier circuit, so that the average current and harmonics could be calculated. And one of my colleagues, who was a very keen railway enthusiast, wrote a program for calculating the behavior of trains drawn by electric locomotives, and giving the amount of power required when to start braking to stop at a station, taking into account the gradients, the weight of the train, the power of the engine, things of that sort. Then on the DEUCE, other colleagues started working. One of them became a specialist in heat transfer and fluid flow, which were involved in the cooling of transformers, which were large industrial transformers which were made in Stafford. And then power system analysis was also started because there was obviously a very close connection between English Electric and the power generators. And the power generators wanted to know how their networks would behave under various circumstances, whether they would become unstable or not. And so work was developed on that, and also on control systems. Now, in 1956, there was an IEE convention on the on digital computer techniques, and in fact, I think 4 papers were submitted from English Electric on various topics connected with the application of computers to these engineering problems. Now, I'd just like to conclude by briefly talking about a development which made the programming easier. I mean, as you've seen, that the programming of the pilot ACE and also of the DEUCE was a difficult job. You had to really get down to the details of the machine. And so a scheme called Alpha Code was developed. There were many schemes developed, but the one that I was particularly involved with was Alpha Code. By today's standard, that was a rather unsophisticated language, if you like, but it had some quite advanced features. For example, by a single instruction, you could order an integration, or the solution of a set of differential equations, or the solution of a set of algebraic equations. And it also had facilities for doing complex arithmetic with complex numbers. So, in some respects, it was sophisticated. And in fact, it made the task of programming very much easier. And so the engineers themselves tended to take over the task of programming rather than giving the job to a specialized programmer, and with all the advantages that have accrued from that, because they were much more familiar with the job that they wanted to do than the programmer would have been. Well, I think that's what I want to say on this, and I'll hand over to you.
Thank you very much, Mr. About the commercial side.
My name is Chris Woodall. I joined George Davis at English Electric at NPL in January 1955 to look at commercial applications, that is payroll and all those kind of things within the English Electric company and indeed outside. And really, what I want to talk, just briefly mention today, is some of the development that took place on DEUCE to make it more suitable for that work and in general to develop it. We've heard, which one is it? Right. Sorry? What's the red thing? The both of them are. Right. As you've heard, DEUCE had just a 32-column card reader punch in binary, of course, so one of the developments was to develop that so it could read 64 column cards, 64 of the column cards, as before in binary. Well, I won't go into the programming of it, but that was that. The next one, from a commercial point of view, was the necessity to be able to read 80 column cards and read them and convert them into an alphanumeric form within the machine. What was done was that each column was converted into 6 bits, and they were stored 10 to a double length word, so that 10 occupied 60 bits, so the other 4 bits of a 64-bit double-length word were wasted, and therefore a full card occupied 16 32-bit words, and the other, there was half a delay line, and the other half a delay line could be used if you wished for output. And that all went into delay line 12, as I remember it. I'd say it's 35 years since I've thought of anything of this, so if I'm not out in some of this, I asked for your consideration. So that took that. The magnetic drum transfers were all from delay line 11. So the magnetic, so programs on DEUCE of a commercial nature tended to get bigger and bigger. And what we had then was that 2 of the delay lines were, of the 12 delay lines, were used for special purposes. So if I come down to number 4, we introduced what we call the A delay lines. So that was 1A to 7A, and they were accessed by use of the P1 bit, which, if you remember from what was said this morning, was spare. So they accessed that, and so that gave us another 7, and that was in a second, as far as I remember it, mushroom. And the first thing that I ever got involved with on pricing, which subsequently became my job within electric computers, was to suggest what the price for those 7 extra delay lines, at 7,000 odd bits, and I suggested that people would be quite happy to pay £7,000, as indeed they were, which I think, if you think of it in terms of what price of computer hardware and computer storage now, it gives you just, again, as I think was mentioned this morning, I think it was, now, who was it? Anyhow, it was mentioned this morning, the way speeds have increased, give you some indication of what happened to prices in the meanwhile. DEUCE itself, in 1955, was priced at, I think I might be saying 50,000. It subsequently came down to, I think, 42,000. The 80-column card reader punch was, if I remember rightly, something like 7,000 to 8,000 in addition, and this was also about 7,000. Come to magnetic tape. This was developed. The magnetic tape unit was taken from RCA in Camden States. They'd had a very long-term association with Marconi's, and so we took that from them. If I remember rightly, and again here in particular my memory of it probably faulty, its transfer rate was 8,000 characters, that's 6-bit characters per second. Obviously quite, again, very, very much less than we have now. As regards the other one, the automatic instruction modifier, DEUCE, unlike the Pilot Ace, had 2 4-bit word stores. And one of the characteristics of DEUCE, of course, is that stores really weren't sequential. That if you went, that you've got a delay line full of 32-bit words, 32-bit words, and then you, after dealing with those, for example, if you had a long matrix, you had to get another set of 32. And what this did was, if you gave the instruction 17 to 0, which meant obey the contents of one of the words in store 17, it typically would be fetch 2 words out of that store. Right. It would typically be fetching 2 words out of that store and putting it, say, from delay line 12 into a double word store 21, on which you would then do your matrix multiplication or whatever. And in obeying the instruction, the contents of word 17, the word in 17, would have, if you wanted to do 2 words, would be the timing part of the instruction would be increased by 2, so that next time you came round, it's moved down to take the next 2 words out of delay line 12 into 21. And of course, after 16 times, you had finished with all the delay line, and you could arrange it so that after 16 times, the modification was carried over into the what's called the wait number, so that you got an automatic jump after 16 times, so that you could then fetch the next part of the matrix into the ley line 12 and carry on. So you've got an automatic counting within it. 17 to 0 worked on an addition basis, if I remember rightly. 18 to 0 worked on a subtraction basis. So this gave you an automatic count, and this, as I say, was particularly useful for matrix type work, and as been indicated, that was one of the major applications for much of DEUCE work. So that was one development. The only other thing I want to talk about briefly, and I've limited my consideration of, sort of, I'd say, programming techniques to things which I'd suggest are probably fairly special to DEUCE for a variety of reasons. And this other one is the use of the instruction, again, like this one, 17 to 0, but say any store could be sent to destination 0 to be obeyed. And typically what that was used for was that the instruction itself would send a different store, a different word to the location N, so that next time you came round it did something different. And the typical kind of application was binary to sterling conversion, where you had multiplication of tens for the pounds, multiplication by 2 for the 10 shillings, multiplication by tens for the shillings, and finally multiplication by 12 for the pence. So that by changing the contents of store N there, you could make the machine do different things in different times round. And this is really possible because every instruction on DEUCE was a jump instruction. And therefore, by doing this, you could make your jump instructions, you could make yourself a tree in this way. As has been said, multiplication was you could trigger it off, and during the multiplication you could do other things. And one of the, I think it was in those days, produced games programs, and one of the ones I produced was the one to produce factorizing of numbers. Now, with a 32-bit word and only a 31-bit divider, there are obviously limitations on this, but you could add things to the divider as it went along if you knew what you were doing and if in special circumstances. And in producing a program to go up to divide numbers or factorize numbers up to 2 to the 40th, which clearly is a little tricky with a 31-bit divider, I produced a system whereby I could add the bottom 11 digits partway through the division. I wouldn't recommend this, but this is what one could do. One would also, by doing a thing like this, add 2, 4, or 6 to the divisor the next time round, so as to avoid factors of 3 and 5. These were the kind of tricks which were got up to in DEUCE programming. I don't think one would recommend them for anybody's use, but they were DEUCE kind programming tricks. I think the more usual one from dealing with at the end of a multiplication would be concerned with things like rounding. But for you did really need to understand the machine to be able to play these tricks. And in those days, I guess many of us had a pretty fair understanding of what went on within the machine. I think that's really all I want to say. As I said, I've tried to keep it to things which I suspect are fairly special to DEUCE, which we wouldn't find on other machines. Thank you very much.
Like Tom, I shall use my punch cards as a source of bacon. I still have 2 left. Is this the last time I shall use them? We move on rather in time. 1956, at a time I think when the thing was ceasing to be fun and starting to be commercial and sordid. There was still an overlap. George showed us a picture of the inside of the DEUCE, and one of my first introductions to it was opening the door and looking in, and I have to say what was going on in there was sordid. So there was still fun. By 1956, however, the degree to which commercial use was possible was coming into the open. I joined really simply as a functionary. I have no idea what the policy was then. I just joined as a programmer. And I did what I was told. And I think that we were very arrogant. And I think that's one of the reasons why the commercial work started the way it did, because it seemed that nothing stood in its way. What someone said, do a stock control system. I had no idea what a stock control system was, so one did it. So when George rang me up and my wife said, it's a voice from the past, I went back into functionary mode. George said, produce a list of all the commercial things that were done on the DEUCE at Stafford, which is all I've done. That one has an interest, picking up from something Tom said. That was probably the first use of a machine to do the design of a machine tool. The cams for a machine to mill out an impeller system for a gas turbine engine had always been done by geometry. That was done then on the DEUCE, and again, as Thomas said, the guy used to take weeks to produce one design. By the time that system was written, heavily using floating point, one of its great features, we turned out 6 designs in a couple of hours, and the guy fell off his stool. So that's probably the first of that use of machine. We then move into straight what I call stock control. The first one I remember in '57 was what we now call warehouse stock control for zip fasteners for ICI. A straight bureau job, input came in from the warehouse, we turned it around and put it out the other side. A very, very tedious piece of programming, but once it was done, worked very well. The same approach then was taken for a set of plumbers' fittings for ICI. This was an example where these were the fittings. 2 ends, a body, like that, a set of rings. And we did the stock control, the warehouse stock control for that, and it's probably a good example where the product, which you still recognise, this one, outlived the program by probably 2 orders of magnitude. There was an example, 1957, of doing scheduling of goods wagons in and out of the crew marshalling yards. Again, a very tedious piece of programming, but it worked. And all these worked very well. We then moved into being more ambitious, and round about then at the meters, relays and instruments division of Stafford Works, making small assemblies. We started off with a successful stock control system. We then moved into something we should never have started, which is scheduling. And that really didn't get off the ground. It struggled, but was not particularly successful. Around about the same time, Stafford Works was embarking down the same track. Did a very good payroll system, did some very good work on what we now call product costing and management accounting. And then both of those started to move into doing what we now call production control, and at that stage began to falter. And I think we saw at that stage that not having either a higher level language or a commercial language of any sort began to make it almost impossible to complete work in the time that was meaningful. And that's why on the list of machines that George produced, you see that the commercial sales of DEUCE really began to tail off. And by then, of course, around about here, we got the IBM 650 coming in, which was a much more practical machine of commercial nature. And I think it all began to die from then. So we were terribly arrogant. I think we did a lot, but the machine had its limitations. Thank you.
My name's Doug Flower, and I joined George Davis's Merry Men in the London Computing Service in 1956. I probably worked as close with George as anyone for a number of years, and it was my suggestion that when, as you saw in your original programme, George was going to talk for 3/4 of an hour, I thought, poor chap, he's going to get such a muddle with his slides. Perhaps we ought to share the load. He did take notice, and so there are now 5 of us talking. My particular area of expertise was what we used, what's now called management sciences, and that was in the London Bureau in the 50s, and I don't think that word even existed then. And much of the work we did was on linear programming. A lot of that was done just up the road from, I think 90% here seems to be from NPL, but about 90% of that work, another of that work was done up the road from Admiralty Research Laboratory as well. And linear programming started off in what was called the simplex method in those days, and I won't go into any details, but essentially it was a way of optimizing things, usually cost, quite often, given various linear constraints. And the example I got there of the animal food mix was if you were going to make some animal food, you had various restraints like it must have a certain fibre content, not more than this and not less than that, and the oil level must be something else, and the nutrient level was some other thing, and all the possible ingredients cost so much per unit. And you had to mix all these things together in the cheapest possible way, so it met the constraints and was done to minimum cost, and that was a typical linear programming problem. And we did this, I remember, for a company called Bibby. I don't know which of these companies still exist, but it was Bibby's, Silcox, and Unilever we did that work for. There was another thing that went along with simplex method, a rather simplified form called transportation. And here, a typical one here, we worked with British Transport Commission, as it then was, on scheduling various goods traffics. Then as time went on, it got a bit more complex, and then you moved into integer programming, where the variables that could, under simplex, take any value, had to become integers. And this was particularly if you were citing, say, refineries, where you couldn't cite half a refinery somewhere, it had to be a whole refinery or none at all, or even 2 of them or 3 of them. You certainly couldn't cite half refineries. So there was an extension to integer programming, which did make the problem quite a bit bigger. And we also did quite a bit of work with the CEGB on what's called quadratic programming. And here's where the constraints and the function you're trying to optimize is no longer linear, but can be quadratic. And transmission losses on power lines are second order, and so we did some work on those. We didn't get all that far with these last 2 because it was stretching DEUCE to its extremes, and it was rather a small machine with big problems. And in fact, the biggest one we tackled was this one, where we had 73 constraints of the sort like, whatever it might have been, I can't remember what the problem was in that case, but some linear constraints, and 110 variables. Now if you work that one out, and George can do this very quickly, I'll tell you it's 8,030. If you multiply those 2 together, there's 8,030 words. And George said earlier it was an 8,000 machine, but he meant the drum was a computer 8,000, which really the drum was 8,192 words. So this took up 8,030 of those words, so you couldn't get the program on. Which is a bit of a disadvantage, but Tom mentioned earlier Scheme B, which is an extremely good package and all these bricks. So what you in fact did was fed the bricks in one by one from the readers you needed them, and just kept the main drum for the data. And each iteration, because simplex is an iterative method, where you iterate to an optimum value, took 3 minutes. And there were 100 plus iterations to solve this problem, which is over 5 hours. And even its very best use wasn't reliable for 5 plus hours. So we had to have a technique that could come out at mid-stage and then feed in again, because otherwise it would let you down. And it reminded me when I wrote those programs, we used to have a thing called grand sum checks, which were there for 2 reasons really. One was to make sure the machine worked. But secondly, when you were doing a thing like this, it was the rounding errors. You had to see were the rounding errors being created beyond what's acceptable. And we set this thing at a value called P8, which if you were working in 23 binary places is a very small number. And if the rounding error at the end of the iteration was more than P8, then it sounded an alarm. Unfortunately, on this thing, it did every time. So you looked at it and said, well, if it's not too big, we'll just carry on. Well, P8 was rather small, but you were dealing with that number of words. I always remember on KDF9 when it came along, the amazement and the debate went on, should we have grand sum checks when we wrote programs? Should we put grand sum checks in anymore? And we didn't. I don't think anyone did after that, but it was very much a part of DEUCE programming. Now, some of the other applications we got involved on here, curve fitting. This was fitting a cube. I mean, again, there's just not time to go through any of these in detail. It's quite a lengthy subject of the this is looking at gilts, the redemption date against the yields. And we worked with a company called Greenwells, who merged with someone who's merged with someone since, and they did quite a bit of work on this as a way of helping decide where to put their investment in. And in fact, when I say I worked with, that's not true, because I wasn't sure of rounding errors again. I came and talked to Bill Clenshaw at NPL, like I was a great expert on this, who assured me what I was doing was probably safe. Next one got down the rather. I was interested in Peter's comment about we moved in 1956 from fun to serious, I think was the word he used. The year before I joined, had worked on guided weapons at the Havilands on analogue computers. And certainly coming to English Lecture LCS was certainly fun then, and I think the fun stayed there. But I know what Peter means. He also talked about the arrogance of us, because we did feel we can tackle any problem. But I think another quality we had was naivety, and commercial naivety. I wrote one program for a firm called Stevens and Howell, who were mixing colours up, and it's a costing program. The DEUCE, you may remember, used to cost £60 an hour. And this took 15 minutes on the computer, so we were initially invoicing £15 every month. Then the word came from on high from Stafford, DEUCE is now £30 an hour. Now I can't remember what year that happened in. So we naively wrote to this customer and said, we're going to charge you £7.10 from now on. Well, this is an incredible thing. Here was the customer absolutely delighted with £15. We weren't told we were going to halve his costs. I don't think George was naive as I was, because he agreed to it. Then the random numbers bingo cards, it was interesting how customers don't change. But the wonderful firm called Plastic Industrial Dartboards came along. They were in 4 sorts of things, and they wanted 4,000 bingo cards, not cards, but numbers that they could put on their bingo cards. And he said the only restriction is that we don't want Mrs. Jones and Mr. Smith to have the same card if they're sitting next to each other, so the cards mustn't have the same number, they must all be different. And that, to him as a user, was the only constraint he had on his problem. But of course, if we'd gone away then, I could have produced cards, and he wanted 15 numbers between 1 and 90. That was the range he had. So I could have produced 114 plus 15, 114 plus 16, 114 plus 17, and so on, easily produced in 4,000 cards. But I don't think that would please him. So in the end, we had another technique, which was to randomly generate these numbers and putting some restrictions on how many each range, and never put the test in to see if they were the same. I hope I'm not telling these stories against George, because we're really quite good friends. We got on very well. When I produced these 4,000 cards and not put a test in, George had a bet with me that 2 would be the same. I don't know whether he'd done the sums or I had, but so he got these 2 trays of cards, which remember there were 2,000 cards in the tray, and went to the sorter to try and demonstrate that at least 2 of those 4,000 cards were the same. But after 2 hours, he gave up. We still don't know. one last thing, where programs haven't changed is in wanting to do things of their own surreptitiously. And I had a thing here called forecasting football results using Ireland values. And a colleague of mine from Marconis at Chelmsford, that wasn't on the list, was it, Marconis? Marconis at Chelmsford, I think that was what it was.
Yes.
Yeah.
Yes.
Yeah.
Also follow-up, yeah.
Yes. Well, we wanted to predict football results, you see, and this is all done unofficially in £60 an hour. It's not too bad. We were letting have a programme at the time. So this was just what the problem was. It was, we were quite interested in football, both of us, and we looked at statistics. And the probability of a home win, we'd found out over the years, was 0.52. 0.52 matches finished up as a home win. And then the required this is what these fixed odds companies used to have. They used to give you 8 games and say, predict the results of 3 of those and get right, you get 12 to 1. And so the required probability of 3 games getting right at 12 to 1 to break even would be if you could get 0.42. Now it looks a cinch at first sight, of course, it's 0.52 at home and 0.42 is all you need to achieve in the forecast. But the problem was, of course, they chose the 8 hardest games. And the chances in the games they chose weren't as high as 0.42. But what we did is we looked at all the results of these games, of these teams who win these games, and not only found out where they were in the league, because that's a simple way, we analysed who they'd beaten and how that other team had got on. So we came out with a sort of ranking order for which looks the best games. And we made quite a bit of profit. I mean, I can't remember what it was in those days, but about £100 a year, which was quite a lot, and you might wonder why I'm not a millionaire. But then this is what happened. They started taxing it. So if you worked out after tax, the probability goes up from 0.4 to 0.47. And we thought, we were getting about 0.45 and doing well. But this ruined it, and we used to get about 12 different coupons. There were all sorts of companies did them. I mean, the well-known ones like Hills, but there was Gibson and Wands and others, there were loads of them. And they wouldn't all have the same matches, so you could choose your best matches out of the 8s and all the others. But then, as I say, this really put the end on it. There's no future. So I'm still here rather than asking questions. Did you want to do something, John?
Thank you very much. We have some time now for a discussion session and questions. And so we will fire away if people have questions.
Could I ask a question before I start, which I thought was going to come up there? The DEUCEs were sold, I said about 33 delivered. Sold is the wrong word, I think bought. English lecturers never had any sales, well, I can imagine sales team at the time, or later on towards the KDF9. I was lost to a colleague there of RE when he was trying to get hold of Gertrude Daisy with regard any assistance from English lecturers doing this of a strictly negative nature. And generally it was quite a battle for people to come and buy their DEUCEs from us rather than the other way around. So that 32 having been sold, or sorry, let's say 33 minus 12, 21 having been sold over that period was quite a remarkable thing. And the last one was sold about 1962, or delivered in 62, and the last one closed down was in 1967, which is quite a story when you think, really, DEUCE's Pilot Ace was designed round about 1947, 1946, 47, before there was any such things as actual working computers. So I think one could sum up by saying it was a remarkable achievement that this went on. And there's something sad about an offshoot doing 400 in the US when we were only doing these penny numbers, but still it's a pretty good achievement and a very fascinating time, and a launching pad for all sorts of things, such as English Electric going on into KDF9 and KDP10 and all that. So we reckon it's coming up. We've got a success story to tell you.
Just before we have any more questions, well, I would like to say that we have got some copies of the handouts, so when people leave, they can pick have questions now. Len?
I heard somebody say behind me, I think, this morning, I don't know who it was, that the science museum has 5 days.
Yes. 5 days, yes.
Is that going out?
Yes, it's up on the upper things, yeah.
Sorry.
I've had my wrist slapped. I wanted to restore it, but I wasn't allowed to touch it. They said I can't.
Could people tell us with the early calculations that were done on DEUCE whether or not they actually got the right result? I mean, you talk about aircraft calculations. I mean, did the aircraft actually fly in the way it was expected? Because my theory is that in almost all cases, the differential equations were wrong or something else. And, therefore, to a certain extent, some of the calculations aren't quite what they're supposed to be.
I say, where maths division was concerned, we never just took the problems that were put to us at face value. We always looked into the physics and made sure that the people formulated them correctly, and also that the numerical methods they suggested were sensible ones. I can remember one case when the company came to me with a whole series of equations with lots of Bessel functions in, and said, can you do that? I asked them what it was. It was actually a problem on the scuffing of gears. Admittedly, it took me some time, but eventually, just for fun, I sent them the answer on the back of an envelope. It was a difficult task, but it just was the wrong approach that they were using. So NPL certainly took the line that you don't just solve the equations that they hand you. You look down a little more carefully at what the problem really is. Am I right, Tom?
Yes, it was very usual to find that was in problems. It was also quite common to be asked to evaluate a formula, which was a very messy formula, and we would do some mathematics on it and find that it was the answer to a fairly straightforward integral. So we would solve it that way and then send the answer on. Incidentally, you may be interested to know that your function satisfies it. They say, oh yes, that's where we start. Quite often, in starting from that point, with a very simple formula, doing a lot of arithmetic, they make mistakes. You find systems which you were sure are the answers to least square calculations, and you find a negative element somewhere. And you can't get a negative element in a least square matrix. So it doesn't quite answer Brian's question, but I think some effective Brian.
On the pilot days, was material left on the drum from one day to the next, or was it just used as temporary workspace? Did you in fact have library material on the drum?
No, temporary workspace only.
No, the drum was recharged.
I'm one of this geriatric piece, and was one of the geriatric monks who managed to make use of pilot aids. It was a straightforward problem. I tried to learn to program the piece, and I've never met such a filthy machine code in my life. But basically, it was a straightforward exercise, originally done for the Coal Board, who were interested in the possibility of knocking down dust with water droplets. So one wanted to know what was the trajectory of the dust particle as the water droplet hit it. A decent piece of impact. Manuel did a lot of work with this in the early days, and other people, Tian Taylor and so on, around aerofoils and similar sections, but nobody done it on spheres. And the problem essentially was a numerical one. It didn't have a formal analytical solution. We passed it on to pilot aids, and a girl there whose name I've forgotten did programming. It turned out a very satisfactory job, and if you remember chap B.J. Mason, anybody remember him, he's noted more for his voice, which penetrates the theatre there. He was at Imperial College interested in clouds at that time of prop. He then became the previous Met Sir Basil. He took the work over and incorporated in his cloud theory, which is the same basic problem of accumulating droplets with falling particles. As far as I know, the work was done fast, it was effective, it seemed to be perfectly satisfactory, there was no analytical check on it, and I was extremely impressed with pilot aids. It's a pity there's a fossil up there. I'm sure Tony Sayer will be delighted to do it.
You're right, it was a big program. In fact, we treated that as a challenge. And it was fun to try and optimise the programme. Really difficult. Like
You're a masochist, though. You're a masochist, though.
Yeah, by comparison with today's programming, it's completely different. But then we were getting such, as Tom said, we were getting such fantastic results by the standards of the day. It was worth the trouble.
Yes, I agree.
On investigating of errors, on the early stages of the LEO project, we used to get a lot of mistakes in mathematical work, which we couldn't check, so we just had to run the program again to see if the answers came out the same. With the variable work, of course, you did accounting checks and you could tell whether the results were right or wrong when you got the answer. Was the same experience found with the case? Did you get a number of cases where the results were just wrong from some machine?
So much, actually. I would say that, rather like today's computers, that when things are going a bit haywire, they generally fell out of the program and nothing happened. I can't remember sort of small errors and things like that ever bothering us. I wonder if maybe it was an I/O problem. It's much more likely that Malcolm would introduce small errors and the program would still appear to run.
I think in our case the errors were probably due to having had AC couplings in the signal paths. You seem not to have had any of those, or very few, and that probably saved having an effect.
So it's not my impression that we got small errors that bothered us in that way at all.
Well, there's a thing that was quite interesting because we got a payroll down. I've forgotten which place it was. But they did the payroll, and they did it themselves, and we did it, and we got an answer, and they got an answer, which was different. So then we did it again, and we got the same answer, and they did it again, got a different answer. And they said they couldn't understand how they got two different right answers.
I can amplify. We did the lab's payroll as an experiment, nothing new in what that was. Tony Dason was. And we included all the warts we could possibly include. For example, if a man on the gate worked on a Sunday, he got extra money. If he worked on Christmas Day, he got extra money. And if Christmas Day was something was difficult. And if a cleaner came up on Saturday and there was no one to supervise, she got a supervisor allowance for killing. So we put in every possible thing. And when we did the dummy run, and there were minor discrepancies, only coppers came. But in fact, the machine was correct, and every discrepancy, it was that the clerical people had rounded some slightly wrong.
We reproduced what may have been one of the last set of mathematical tables for the Royal Society, some remarkably esoteric function. And we made a special printer just to prove them out. Yes. Those were very carefully proved that, and in fact an error was found in them, and that proved to be due to the people on the LISO machine noticing that one of the figures was damaged and touching it up and putting the wrong figure.
One or two speakers have commented on punch cards and people saying, looking at it from the business use of pilot ACE and DEUCE, one important fact was use of punch cards as a backing stock, where in clerical use generally you have large volumes of input and output and comparatively little actual computing. But you do have a lot of sorting. And obviously, with machines as proved as they were, you had virtually no opportunity to sort large masses of data. But officers were used to the pre-computer punch card installations, which of course were very good at all the sorting and correlating of punch cards. And this was a major factor, really, in the clerical use of machines like ACE and also the machines that led to the whole ones on punch cards. And with paper tape, of course, it was much more difficult. It was also much easier to amend punch cards by the well-established custom of putting the chat back.
Yes, I've still got a
putting
back
it
through now.
this was important for creating data, but it was vital when it came to amending programs, because I defy anybody really to punch up a set of 5 cards, 12 bytes binary, get them all backwards binary. The other aspect of it at Teddington was that in those days, as somebody mentioned, you did demonstrations. You could never have a demonstration that went wrong, because all you could produce was punch cards. You had to take them upstairs to be reproduced into readable form. And invariably, upstairs, you had the correct pack of cards.
I've done that on live television.
Yes.
May I ask what sort of level of uptime you had and how much engineering support you had on each of the machines?
The custom on DEUCE, I mentioned the marginal checks that were. Did I know? That was something that I left to somebody else they didn't do. Although DEUCE was functionally very similar to Pilot Ace Tidied Up, there were some changes in the engineering. One was much more thorough introduction of marginal testing, so that you could use that for locating faults, and also by being able to move all of the points on a particular voltage level simultaneously, the odd volt or two up or down to make sure it still worked. You could give a level of confidence. And there was systematic tour inspection, you might say, which tended to take about 2 hours a day of the machine's time in some installations, going round this regularly and making sure the thing was in really good condition. And it was a very reliable machine. I think it owed quite a lot to the introduction of marginal checks and to that sort of regime.
Can I make a comment on that? One of the, people haven't talked much about reliability of valves. Everybody talks about cathode failures, heater failures. In fact, that wasn't the main problem with these ECC 91s. They had a bow window grids, which were very, very close to the cathode, and little bits of oxide or something would fall down and get between the grid and the cathode and rest there, so when you tap them, some sort of pulse would go in. The thing would appear to be working correctly. You tap the valve, a little pulse would get in. These were called tap-happy valves. No problem. So we used to go around tapping these valves. Well, I thought, what a terribly crude thing. I mean, we're not engineers, we're just sort of playing games. I was visiting IBM at their factory in somewhere in New York State. They were building their first magnetic drum machine, 650, was it? 650, yeah. And they had this great big assembly line. All the engineers were wearing black suits in the way they used to. And then at the end of the line, there was a man with a carefully calibrated hammer. Oh, we are engineers, aren't we?
In terms of reliability, I think by 1953, which I guess after 1 year of operation, we were getting the power days at about 10 o'clock in the morning and running from 10 o'clock at night. And I seem to recall figures about 70% reliability. We had a strict rule, the engineers didn't have the machine during the long day. Unlike the claims where I think the engineers had it during the day, and the poor user had to go in midnight hours.
Right, I think we'll call that to a close now. We've had a very long and an extremely interesting day. Certainly I find it very fascinating. I would like you all to join me in a thanks to George and the team who've given us an excellent day. And there are some more copies of these handouts coming here. Thank you very much.
Could I say there are also some blue folders, or if there were. Know about NPL.
Are you heading home, motoring? Eventually, we'll taste the stock. I think it's not that. If we're doing it even up, since it's a bit earlier than normal, I have no idea when Well, Tony Sell will eventually edit it together.
It'll be available.
Yeah, it'll be available. They're all available as our audio of the whole.
Mr. Sinclair, I used to work on either 802s or 803s, and I can't remember which one was which.
803.
Which you've got an 803?
803, yeah. 803B. That B means anything.
I don't remember. The one
I don't know what 803 is.
Ah, in that case, perhaps it was an 803 then. Has it got? Is it the one with the 24-volt nickel cadmium battery?
Yes.
It's about so big.
Well, no, the battery.
No, the machine.
The cabinet. The cabinet.
Right. Well, I haven't seen it for 20, 30 years. So.
Can I just say that our next in-steam day is on the 2nd of June. The in-steam day, for those who don't know, in Lancashire, is when we attempt to get some of the old computers that were working mostly we succeed, and that's an all-day event from 10 till 5, just drop in and you may find the machine working.
Yeah, I'm not here. Every month.
Okay.
Yeah, I'd love to come and have a look at it, see if it's the same machine, because if it is, I did a lot of design work on it. I designed a large chunk of the power supplies on it. Yes. If it's the machine I think it is. And the machine I worked on, 24-volt NiCad battery.
26-volt battery, yeah.
Yes, 24 volts, a SAFT NiCad battery. It was an aircraft battery.
Yeah, and it's on a hinge door.
That's right.
One end of the battery.
That's right, and it sits in a little pocket so the fumes don't get into the rest of it. Ah, well I know all about that machine. I know all about the power supplies. Right.
Every first Wednesday of the month it's open if you would like to come.
I would love to come. Yeah. No, I've just filled in the form because I've just done that. Let me have a look. I can't do it on the 2nd of June because I'm on holiday.
You don't have to make an appointment.
No, hold on. 2nd of June, let me see.
If you want to come.
You say the first Wednesday in the month, so it'll be the 7th of July. Right, let me make a note of that.
The best thing is to give Tony Sale a ring.
Yeah.
His phone number is on the bottom
I've got
of
it.
that, right?
Yeah.
Just say you haven't been before. Could he tell you how to find it?
Okay, in the same day.
That he will give you the directions.